Let's talk about more about this balance tree to make sure that this we can achieve a certain performance. So balance tree is this one. The H-1 level, we have a full tree, and H level we have at the same level, leaves at the same level. So if we can draw the diagram, it looks like this. Upper side we have a full tree, right? And down there we have the same level leaves, right? And if the size of n, we already discussed this inequalities in the previous one, right? So for example, these 6 nodes, the height is 0, 1, and 2, right? And then its maximum value of the nodes, its maximum tree size is determined by this equation, right? So 2 plus 1 minus 1 is 1, 7, right? It's going to be, this one is going to be 8, and minus 1 is 7, and it's going to be less than n. And if n is equal to 7, we are going to call it a full tree, right? And here, we can store up to 7 nodes here, but we have only 6 nodes, 1, 2, 3, 4, 5, 6. And the empty space is around here, just 1 node here. So if we count this one possible content here, 1, 2, 3, 4, 5, 6, 7 nodes, and then we can store up to 7 nodes. And at the same time, if we have 0, 1, 2, 3, 4, 5 height of tree, then we can store up to what? 67 nodes, and here this space is 67 minus 6 is 57, right? 57 nodes are not used. These are not used. 57 unused spaces, right? And what you want to do is we want to remove all these unused space, and we only want to have some unused space at the last level of this tree, and that's the balance tree's definitions. And in that case, let's imagine this equation, these inequalities. So we have a certain, sorry about this, we have tree of a certain height, and its tree height is, let's call it h, and its tree size is going to be n. And we know for sure n is going to be less than or equal to 2h plus 1 and minus 1, right? And then its full tree structure, upper side is going to be what? It's going to be the this full tree size is going to be h minus 1's 1 tree height full size is going to be 2h minus 1 and plus 1 minus 1, and it's always going to be, right, we'll have some additional nodes here, so it's going to be not equal, smaller than the current tree size. And then in the case 2h minus 1 and n 2h plus 1 and minus 1, this case, right? So this imposes this the first part of this equation imposes the full tree structure of the upper side, right? Of the upper h-1 levels of the tree. And this full tree structure conditions comes to this first part of the equations. And let's see how it works with the real values. Let's see how it works with the real values. And if we compute the 6 nodes in a tree of height 2, and in this case, we have 2 minus 1, it means that's 3, and it's going to be 7, right? And the number of nodes n is 6, right? And 3 is smaller than 6, and 6 is smaller than 7. So this equalities works all right, right? These are all true. However, this structure, which doesn't have a full tree structures in the upper side, it is not full tree here. And in this case, 2, 5 minus 1, it means that we have 0, 1, 2, 3, 4, 5, right? 5, height of 5, and h is 5. So here 2, 5 minus 1, and 2, 5 is 32, and minus 1 is 31. And 2, 5 plus 1 minus 1 is 63, right? So this satisfies. However, this is incorrect. This is false statement. So this is going to be wrong. And in this case, we know that we don't have full tree structure on the upper side, and it's going to be the unbalanced tree, right? So this is a short examination of whether a tree is a balanced or not. And here we talked about the full tree, and you also know this structure of the complete tree. And complete tree is balanced tree. Yeah, right. It's an interesting question, right? So complete tree is, it has a full tree, and it's going to be peeled up from the left side to the right side, and it's going to be the complete tree, and always going to be peeled from the left side. And actually, it's the balanced tree, yes, because the upper triangle is the balanced structure. However, balanced tree is the complete tree, and this is the obvious example of the counter example. Upper side is, yes, full tree. However, it's not always going to be filled from the left to the right. It's going to be filled in the last layer without an order. And that's the violation of the complete tree. And balanced tree is not always complete tree. So complete tree is always balanced tree, but balanced tree is not always complete tree. So that's the arguments and understanding of the balanced tree. And why we studied balanced tree is we want to achieve this tree-based implementation performance here, but we are going to fail that if we have the unbalanced tree. And to achieve this performance, we need to make tree balanced, and that's why we studied balanced tree. Okay. So after doing this binary, we are going to understand and implement binary heap. And binary heap is a perfect example of the balanced tree and how to make tree balanced. And we are going to study this in the second part of this week. Okay, thanks for hearing and have a good day.